Welcome to this video. It gives a overview of the distributed couplers and power dividers design and simulation software from orifhammer.com. You can go to the website and download the software, save the exe and the icon file on your PC, and it should run on all standard Windows 10 PCs. Right, so the first window that opens when you run the software is this window. So it gives you the capability to select between 90-degree couplers, 180-degree couplers and power dividers. Remember, this is distributed couplers and power dividers, so that means that uses transmission lines, distributed elements at high frequencies where lumped elements won't function any longer, and it then calculates the electrical length and electrical impedance components of the couplers and power dividers. Right, so couplers 90 degrees, here we have a branch line coupler and a coupled line coupler, which are 90 degrees. We have a standard rat race coupler, which is 180 degrees. And then for power dividers, we have Wilkinson power divider, but it can be a multi-section from 1 to 8 sections for wider bandwidth, but with equal power division. Let's have a look then at a branch line coupler, a 90-degree branch line coupler. So we can click on that and we can click run. Right, and here we have the design and simulation of a branch line distributed 90-degree coupler. We have 4 windows, so in the input you can input all your input parameters. Here we have the simulated results. The frequency response is plotted. We can select between coupling, match and phase. Here we have the circuit diagram. And here we have the calculated component values of the coupler. So here we have the impedance, electrical impedance, and the electrical length. So for branch line coupler, if we input a signal at port 1, then the coupled ports will be port 2 and port 3, and port 4 will be the isolated port. Right, so the input parameters, we have the frequency, the center frequency, we have the coupling, in this case it's 3 dBs. We can change the coupling to any value to get different coupling values. You can take the attenuation factor into account of the transmission line, the characteristic impedance, 50 ohms in this case. For the plot, you can stipulate the stop and start frequencies, a number of frequencies, and a marker. So over here we have a marker which we can move around. So for example, we can go have a look at the marker at, say, 7 gigahertz. Right, so there are the values at 7 gigahertz. We can have a look at the match. Let's have a look at the match. Okay, S11, and we can have a look at the phase. So there we have the phase. Let's go back to the coupling. Okay, for this case then we have calculated the value of this transmission line, Z1. In this case it is 35.35 ohms, and Z2, the transmission line there, is then 50 ohms. Okay, so we can then go to any coupling. If you want a 10 dB coupler, we can go to 10 dBs. So there we have a 10 dB coupler. Let's put this back to the center frequency. Okay, there we have a 10 dB coupler. We can make the attenuation factor 0 as well if we want to. Then we get an exact 10 dB value. Okay, so that was the branch line coupler. We can also then go to a coupled line coupler. So this is just then coupled transmission line. So we would have a even and odd impedance. So we have an even mode attenuation factor and an odd mode attenuation factor. The rest are more or less the same. In this case we have a 10 dB coupler, and then the program calculates the even odd mode impedance and will give you the frequency response. So in this case, the coupling then, if we put a signal into port 1, the coupled ports would be port 2 and port 4, and port 3 would then be your isolated port. So that's what we see here. This is the power coming out at port 2, power coupled at port port 3, sorry, at port 4, and then the isolated port is port 3. So we can have a look at the match at the input, and we can have a look at the phase. Right, so those are the 90-degree couplers, the 180-degree couplers. We have the standard rat race. So in this case, we have very similar inputs. The frequency response is similar. We can calculate the impedances and the electrical lengths of the transmission lines. And in this case, if we put a signal in at port 1, we're going to get coupling out at port 2 and port 4, while port 3 will be then the isolated port. So we can once again change the coupling to whatever we want to, 15 dBs. Okay, and there we see we have then coupler, 15 dB coupler, rat race coupler, and with a coupling then at, in this case, minus 15.06 at port 2, and obviously if we make that 0, then we should get exactly 15 dBs of coupling, which we see over here now. Right, we can have a look at the match, and we can also look at the phase. Okay, so we see we have a 180-degree phase difference between the coupled ports now. Right, then we can go to power dividers. So we have the Wilkinson power divider, multi-section, equal power division. We can run that. In this case, we have a 4-section power divider. So we can see, we can also, in this case, we can also stipulate the bandwidth. So over here, that's the relative bandwidth. So it's the upper and lower frequency divided by the center frequency, and that's the relative bandwidth, and then the results will be calculated for that specific bandwidth. Okay, the bandwidth is only relative or applicable to multi-sections, in other words, a section greater than 1. So in this case, it's a 4-section, and we have a 1.2 relative bandwidth, and it's equal split, so equal power at ports 2 and port 3, which we see over here, in this case minus 3.12, and over here we have the isolation between ports 2 and 3, so that's the red curve, is 3.2. We can see the match at each port, so there you can see the match at port 1, which is a blue, and then port 3 and 2 lie on top of one another, the red and orange curve, and then the phase between the output ports we can also have a look at. So let's have a look at the coupling again, and we can see obviously there's a trade-off between the isolation and your match versus your bandwidth. So if we look at the match S11, if we make the bandwidth smaller, let's make it 1, a relative bandwidth of 1, then we're going to have a better match and better isolation, and a better match, as we've seen. And if we then make it larger, obviously the match S11 match and other ports as well is going to start degrading. The isolation will also start degrading, and if we make it too big, then we're going to get a message saying reduce the bandwidth, due to the fact that the calculation is going to start becoming inaccurate. Okay, we can go up to from 1 to 8. So let's go to an 8-section power divider. We can run that. Okay, here we have a bandwidth of 1.5. Let's change that to, I don't know, 1.6. So look, so it's going to degrade slightly. The match, let's have a look at the match. Okay, so there we can see the match, minus 25 dBs at the center frequency. You can see it's got 8 dips, 1, 2, 3, 4, 5, 6, 7, 8. 8 dips. And the isolation is then also sitting around about minus 26.91. Okay, yeah, so obviously if you start making the bandwidth too large, then it's going to give you an error. See, okay, so we have to reduce the bandwidth. So, I don't know, 6.5 might work. Okay, so there we have a relative bandwidth of 1.65 with 8-section Wilkinson power divider, and we can then see the design values and the frequency response. Over here we have a slider so that we can see the complete circuit diagram if you want to, and over here is also a slider to get all your circuit component values. Okay, so that was then the case of distributed couplers and power dividers. There's quite a bit more software available at rfhammer.com, which you can have a look at. So thank you for watching this video, and don't forget to visit rfhammer.com.